Okay, so on, this is the, this video is going to be the back side of notes 13, properties of intermolecular forces. Let me just write this here, back side. And what we're looking at for this part is we're going to look at heating curves. Now, this is what gets confusing because people get phase diagrams that are actually curvy confused with heating curves, which don't have a single curve on them at all. So this is the heating curve, and all it does is it has 5 portions on it: diagonal, straight, I guess flat, diagonal, flat, diagonal. Those are the 5 sections. And what this is we're taking a substance, we're either heating it or cooling it by adding or removing energy or heat. And here are the sections. So the very, very bottom section, from like wherever it extends to, this is where solids are, liquids, gases. Solids, liquids, gases. So here it's showing this is the heating curve of water. This is water in its solid phase, liquid phase, gas phase. The flat lines are the actual phase changes itself. So this is melting and vaporizing, aka evaporating. Notice on this axis we have the temperature. The temperature as we go up increases, and this is just kind of like our as our progress axis. So our solid, we're adding heat, the temperature is increasing, and the solid is getting warmer, 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 warmer. Doesn't matter if we're down here at -30 or up here at -10. Doesn't matter. As long as it's still on this line, it's still a solid. It might just be a warmer solid versus a colder solid. Same thing with liquid. Doesn't matter if you're here versus here, cold liquid, warm liquid. The solid has to get warm enough that it reaches its melting point. The melting point of water is there at 0. So that's what this line is showing. The flat lines are the melting point, and the boiling point will be up here. Once we reach where we're getting warmer, solid, solid, getting warmer, and once we reach here, notice we're not actually getting warmer. So where's all this heat that's being added going? Because right here it's being used to like heat up the sample. So what the heck's happening to the heat that it's not cranking up the temperature? Temperature remains constant during a phase change like melting or boiling. So what's interesting about this is on the diagonal portions, the energy is being used to heat up the sample. But on the phase changes, the energy is instead being used to overcome the IMFs, the intermolecular forces. We can't go towards 2 things at once. We're either cranking up the temperature, or we're overcoming IMFs. Cranking up the temperature, overcoming IMFs. Cranking up the temperature. Remember that phase changes are physical changes. We're not breaking bonds. We're not forming bonds. No new substances are happening. It's not a chemical reaction. We're literally just overcoming the IMFs, saying, like, do the IMFs keep it together in solid form, or is there too much energy that it's a liquid or a gas? So there are a couple equations that we are going to use when doing heating curve calculations. On the flat portions, which I did in pink, so I'll highlight this in the same color. The flat portions, we're going to use m times delta H as the formula. And the diagonal portions, we'll use MC delta T. So on the flat portions, M in all cases is going to be like the mass, how much we have of something. It's either mass or moles. You could convert mass into moles, but this is the amount, the mass, the moles, the substance that you have. And your delta H stands for enthalpy. And this is basically the heat of the phase change. When you're melting, we deal with delta H bus, which is stands for fusion. That's like the old term word for melting. And delta H vape is either evaporating or vaporizing. And those are what we're going to use here. So when we're doing the melting portion, it would be M times delta H bus. But up here, it would be M times delta H vape. Diagonal portions. As the sample is heated, the mass, M, this specific heat, C, and the change in temperature are factored into the equation. So this is either the mass or the amount of moles that we can convert. Delta T is the change in temperature. For example, delta T for this liquid line goes from 100 up top to 0 down bottom. Your delta T would be the difference between those values. And the specific heat is basically a substance's ability to retain heat. So when you are cleaning out the dishwasher, let's say, for example, mom says, go clean out the dishwasher, and you're like, okay, whatever, and you're cleaning it out. And if you you open it, steam comes out, cool. If you go straight to grabbing glass, it's really, really hot. If you go grab like plastic, it's not hot. So you can put the Tupperware away while the glass is cooling. But why is the glass so hot and the Tupperware not hot if the water in the dishwasher was the same temperature, right? It's not like hot water was going on the glasses and the cold water was going on the Tupperware. Same temperature water on everything, but certain materials, maybe the silverware would be pretty hot too, but not plastic. And that's because of the specific heat. The specific heat is just how well a substance retains its heat. So we have to look at just kind of keeping that in mind. So it seems complicated, but let's try it out. It's actually not so bad. So down here, example of a cooling curve. Ooh, cooling curves. Okay, cool. I actually, do I want to do this one? Let me think about it. Hold on. Okay, it's fine. We'll do it. It's just a little bit tricksy because it's a cooling curve. So instead of going warmer, 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 we're going cooler, 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 but it's fine, same math, we're in AP Chem, we can do it. One thing I want to do though is we got to get rid of the Fahrenheit temperatures and convert them into Celsius. The reason being, this graph is given to us in Fahrenheit, but in the table over here, we've got joules per gram Celsius, joules per gram Celsius, joules per gram Celsius. It's gonna be a lot easier to just fix this than to convert this. So the problem says, calculate the total heat energy in joules needed to convert 60 grams of substance X, this one, from 200 degrees Fahrenheit to 25 degrees Fahrenheit. Show your work below. So we're starting here at 200 degrees Fahrenheit, and we're going to be stopping at 25 degrees Fahrenheit over here. Let me write in 25 degrees. Okay, those two numbers are significant because this is where we're beginning and this is where we are ending. There are also two other points that are important, and those are the flat lines, the phase change portions. So this one is at 125, it looks like, here. And the other one is at 50. So I need to at least convert those four temperatures into Celsius before I do anything else. So I did these conversions here. I didn't really worry too much about them. I just went to Google and did like convert Fahrenheit to Celsius, and was like 25 degrees Fahrenheit is -4. 10 degrees is negative, or let's see if I did that wrong. 50 degrees is 10. 125, and I just got all of these here. So the 200 I converted to 93, 125 to 52, 50 to 10, 25 to -4. These ones are the ones we're going to be using. They are in degrees Celsius. All right, so for the first part, we're beginning here. And that's going to be our first section. We're starting out hot and getting colder, colder, colder. So this is our section where we are a gas, right? That's our gas section. And then the next diagonal will be the liquid. It's the exact opposite of this one, where the gas was at the end, because this one is a heating curve and this one is a cooling curve. So gas, diagonal portion. Formula for the diagonal portion is MC delta T. So I'm going to call this, I don't know what I'm going to call it. I guess I'll just leave it. But this is Q, the heat of the gas section. The heat of the gas section equals MC delta T. I just got it from right here. The M is the mass. It tells me that it's 60 grams. That's M. C, I'm going to come up here and get it from the table. I need to use C of the gas state because that's the section we're working with. 2.3 joules per gram Celsius. And the last part, delta T, is the change in temperature on this section. I went from 93 down to 52 degrees Celsius. 93 minus 52 degrees Celsius. Equals 5658. If you look at how everything cancels out, you'll see that we've got grams, grams, Celsius, Celsius, and the only thing left here is joules. So my answer is the heat of the gas state, this section, is 5658 joules. Next part, I'm moving across from here to there. This is a flat section. This is the phase change between a gas and down here will be liquid. So Q of the phase change, let's see, normally this would be evaporation, but since we're going backwards, the opposite of evaporating would be condensating. So I'm just going to do COND. The heat of oh, this is so confusing. The condensation would be, I'm going to copy paste this M delta H. And I'm still going to use delta H vape because even though it's not evaporating, it's going the opposite way of evaporating, it's condensating, it's the same value, right? It's the same process, just backwards. So the mass stayed the same. It's still just 60 grams. And I'm going to get delta H from the table here, 198 joules per gram. Equals 11880 joules. So that's how much energy is associated with going from here to here, getting it ready to be a liquid, that phase change. Okay, next section, kind of getting the hang of this hopefully. The next part, diagonal from here to there. This is the section where we are a liquid. Diagonal portion, copy paste this formula. Q is the heat equals MC delta T. People always ask, like, why is heat Q? I don't really know. Like, they just came up with that. So, not sure. Q of the liquid state equals MC delta T. Mass didn't change, it's still 60 grams. The specific heat of the liquid I'm getting from the table. I just have to make sure I pick the right one and get C of the liquid state, just 2.7 joules per gram Celsius. And the change in temperature is only from here to here, just that region. From 52 down to 10 degrees Celsius. and I'm getting 6804 joules for this one. I guess I could have labeled that. That's the heat associated with the liquid portion. Okay, I'm gonna really quick go through the last little bit. 2 more sections till we get to the end. We've got to do this flat section, which is freezing from a liquid to a solid. And then we've got to get from there to just there, not all the way down the paper, just to where it told us to end in the problem. So the heat of freezing, I guess, or the heat that's associated with melting / freezing is M delta H. Fusion is the old time word for melting. And even though it's freezing, melting and freezing are the same process, just backwards. We still have 60 grams of substance. And I'm pulling the delta H bus from here, 142 joules per gram. And 8,520 joules. Last diagonal part from here to here. This is the solid state. The heat associated with the cooling of solid. MC delta T for the last time. MC delta T, MC delta T, MC delta T. The mass is still 60 grams. The C value from the table, I pick the one that's C solid, 1.5 joules per gram Celsius. And then the temperature change, but just for this baby section, is from 10 down to -4. So think this through. 10 all the way down to -4. 10 minus -4, that's 14, not 6. And I'm getting 1,260. So all of these together, all of these together are the energies associated with the 5 sections. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So if I need the total heat energy, not just the energy of the little sections, I need to add all of these together. So I just added this plus this plus this plus this plus that, all of them together. And the heat total is, I'm just gonna write the process. It's the sum of all parts. And when I added them together, I got 34,122 joules. Now here's the thing. This is the heat energy for that section. And usually they want it in kilojoules. So to get from joules to kilojoules, we're going to divide by 1,000, which would just be 34-ish kilojoules, just to keep it simple. 34.122. So even though the problem says how much energy is needed to convert this, this isn't energy that's needed on the cooling curve. This would be the energy that is released, because we're starting at this high energy up here and we're working our way down. This is actually the heat that's released from the sample. Okay, so let me zoom in just a little bit. So if you need the whole page, you can get, or at least this problem, then you can get that.